All right. Thank you for the introduction. Thank you for the invitation. It's a great pleasure to be at this wonderful conference in an excellent venue. Today, well, we heard already about systems for quantum computing, and one of the rising platforms for quantum computing are Rydberg atoms. However, I will now touch upon a different aspect of Rydberg atoms, which is their applications in quantum metrology, in particular, metrology of electric fields. And in fact, atomic systems are very well known for magnetometry. Here we'll be looking at electric fields, how to sense them using a various range of protocols. So, in fact, in the picture here, you can see a cold atomic ensemble, and this will be the main object of the second part of the talk. But I will start with a little bit of hot atom systems as well. So, we come from the lab at University of Warsaw, affiliated both with the Faculty of Physics and the Center for Quantum Optical Technologies, which is an international research agenda. We are a small concentrated team, and in fact also Bartek is also today here. He had a poster yesterday, so if you want to talk more about especially the cold atom system, we're happy to talk more. So starting with the hot atom systems, it may be surprising that, well, you usually think that Rydberg atoms should be probably very fragile. The electron is excited to a very high lying state, so perhaps it can be very easily ripped off and the atom gets ionized and the system is not useful for the Rydberg atom physics anymore. Well, that is both true and not. And in the hot atom systems, the things seem very chaotic. We are at room temperature, the atoms are moving very fast, and yes, they will also collide. They will collide with the walls. There will be some impurities. However, if you simply take a vapor cell and you take lasers to excite some atoms to the Rydberg states, and you're not going to really be able to excite too many of them because they will start colliding too much, you can still get a pretty strong spectroscopic signals with Rydberg atoms. And those spectroscopic signals will be very useful for using those Rydberg atoms. And what do we want to use them for? So the Rydberg states have a broad collection of transitions between states, let's say, for example, like NS and NP, or NP n-1D, ND n-1F, and they form very nice branches of transitions that quite densely cover the very interesting range of frequencies from the singular gigahertz range up to several terahertz range. And especially even though maybe it's a little bit less dense here, but you can still find more transitions, but the coverage in the hundreds of gigahertz range is extremely interesting, as it is a very difficult range for conventional electronics. And not only the Rydberg atoms have those transitions, they are also very strong. Uh, it is true that you get higher dipole moments for higher quantum numbers n. However, they grow as n squared, but you can also get very strong dipole moments for lower n transitions. In fact, we are talking about dipole moments that are a few hundred, or maybe even sometimes for the higher states, tens of thousand times stronger than the transitions between states like 5s and 5p in rubidium. So the ground state and the first excited state. There it's like 1 EA0 is the dipole moment. Here we are talking tens of thousands down to a few hundreds for the lower lying states. So very strong transitions, hence a potential for great sensitivity. If you can get such a nice sensitivity in those peculiar ranges, you can think about very interesting applications. First of all, we can make devices that use atomic vapors to detect or image very sensitively uh, radiation at unconventional wavelengths that are difficult for conventional electronics. We can also think about detecting radiation at the single photon level. So very weak radiation, for example, in space, it seems very interesting that you can use the atomic ensemble as a frequency converter between the gigahertz and the optical range. And we are also exploring, together with the European Space Agency, various applications in microwave ranging, sensing, communication, etc. But how the how does the detection exactly work? Unfortunately, there is no one simple answer. We are now exploring several different detection modes. One of the most traditional and first explored mode was just an observation of the Outler terms splitting induced uh, by the microwave frequency. So then you would have two spectroscopic lines in the laser spectroscopy signal of the vapor cell that would be split by the amount which is the Rabi frequency of the microwave. Which is very interesting for calibration, but not so sensitive. To get more sensitivity, you need some kind of local oscillator, and you can get it by another microwave field, or in our recent paper, we have developed a local oscillator that is only driven by other optical fields. So we can just turn on additional lasers and suddenly we have a phase sensitivity. So this tiny signal here on the GIF becomes very noisy. But today I will speak a little bit about the type of detection, the detection style, which involves upconverting the radiation using atomic transitions in a wave mixing process and then simply counting the photons. But overall, there are even more methods, such as also, I haven't even yet considered the very simple attempt to simply just try to observe Rabi oscillations induced by the microwave. I will tell about that later, but please, in general, stay tuned. We are working on a review paper in a nice collaboration led by the Space Agency, in which we are exploring different methods and their applications in space technologies. But now, for our particular realization, we use a six-wave mixing process, which involves 3 different lasers, and then a microwave field gets absorbed, while a signal photon at 776 nanometers, a very convenient wavelength to be detected, gets emitted. And we are able to use photon counter to detect those photons, and it has a very nice dynamic range from the level of very low intensities to intensities that are already very detectable using other methods. So here, when we have the saturation, this is in fact where we already get the nice Outler-Tan splitting. So we can nicely calibrate our field because we know the dipole moment from Fourier considerations. On the other hand, when we attenuate, we hit a floor at some point, and it turns out that this floor is much higher than the intrinsic noise of the detector, of the photon counters, etc., that we are able to calibrate. And we were able to figure out that, in fact, this floor quite nicely matches the level of thermal radiation that you would expect. So you can calculate it from 2 different considerations. First of all, you calibrate using Outler-Tan splitting, and then you know your attenuation. On the other hand, you can simply predict what's the thermal radiation level at 300 Kelvin. That's just thermodynamics. So we did several more considerate experiments that try to prove that this is indeed the thermal radiation, but one that usually convinced me was the fact that if you now convert the broad, almost white noise thermal radiation using a narrow atomic line, which is then you get a noise spectrum which is proportional to the transduction bandwidth. So we can measure this transaction bandwidth. We can apply the Wiener-Khinchin theorem to get what will be the G2 of this function. So of course this gives us the G1, and then G2 is 1 plus G1 squared, and this is exactly what we get. So and the G2 here was about 1.6 to 1.8. Since then, since this paper, we've been in fact able to improve the G2 such that it is almost statistically not distinguishable from the from 2, which you expect from a perfect thermal state. All right, so those are our most important results for the hot vapor system, which turns out to be very sensitive, but it does lead to several difficulties in trying to understand what will be the ultimate limit of this system. So in fact, in magnetometry, for example, people are able to identify particular noise contributions like shot noise of optics, projection noise of the atoms, etc. In here we already started seeing so many different methods that it is not exactly clear what is the limitation in one method or the other. I mean, here we are doing a frequency conversion, so we are really limited by the efficiency of this frequency conversion, which obviously does depend on how many Rydberg atoms you have, but is this hot vapor system doesn't allow you to really nicely pin down the fundamental limitations. Therefore, we decided to also do those kinds of experiments with cold atom system, which offer us a simpler system to model without much chaos that happens in a hot vapor cell. Also, no Doppler broadening, which simplifies the atomic calculations, and the ability to shape a certain concrete atomic sequence in a typical quantum metrology way, where you prepare some state of the atoms, you measure the microwave field with the atoms, and then you try to evaluate the state. Well, make a tomography, measure the state, estimate, etc. So to understand how the cold atom system works, let us come back for a moment to the ground state quantum memories, which I've been working on during my PhD. So in a ground state quantum memory, you can store a photon, for example, using a two-mode squeezing interaction, where you scatter one photon and you create a collective spin wave excitation, which is an excitation in a cloud of atoms where the single excited atom, it is excited to another part of the ground state, a metastable state, another spin state, is delocalized. So we don't have the which atom information, therefore the state is nicely immune to atom loss. However, we also like to care about the phases here, and the phases here encode the positions of those excited atoms. That's simple, but there is also some k vector. And this k vector is in fact the difference between this optical beam and this optical beam. And we call it that this is the wave vector of the spin wave, and this will be important. We can later retrieve the excitation, and again, this k vector will be restored. The k vector will be restored, and the photon number statistics should also be restored. So now this k vector also is very much related to a decoherence. So now imagine a certain classical analog of this system where we store a strong coherent state in this atomic excitation. Then we don't need to care about such collective states. We can simply write that a certain ground state atomic coherence has some off-diagonal elements that have a certain coherent amplitude and a spatial dependency. So now if you pinpoint those phases or those phases on specific atoms here, then you get a nice spin wave. So this is a periodic color map with a spin wave shape. However, now if the atoms move and they do not diffuse away, they have simply, in this system, it is simply a ballistic motion at a finite temperature, which is of the level of, let's say, more or less 50 microkelvin. So when the atoms move, the spin wave gets diffused. And in fact, you can see that this happens way quicker than the entire cloud is still a hole. But the spin wave is very dense, and then you get the system is decoherent. So you can see that this is kind of like each atom keeps its phase. So in a way, the information is not fundamentally lost here, but it is diffused away, and we are not able to have a phase matching condition at readout. And the lifetime is inversely proportional to the wave vector of the spin wave, also to the square root of the temperature. But our idea is that we should care for the wave vector to try to improve the lifetime. And well, The lifetime has never been much of a problem in the ground state atomic system, because then the typical wave vector of the spin wave has a wavelength of 2 centimeters, huge, much larger than the atomic ensemble, not a problem at all. But this is unfortunately not the case in a typical Rydberg atom system, where this metastable state is no longer in the lambda configuration, but in a ladder configuration. So we have a Rydberg state here and the ground state here, and we climb up to the Rydberg state using lasers at 780 nanometers and 480 nanometers. And unfortunately, then the wave vector of the spin wave, those phases, are at the level of which has a wavelength of about 1 micrometer, which is pretty dense and leads to the decoherence in all previous experiments within about 1 microsecond. So that's a problem. How do we deal with it? What do we do typically? So this is our typical configuration. We store several hundred of photons, maybe tens of photons, using this EIT style configuration. And then after a time delay, we just apply the blue laser and the signal gets retrieved. Now, to deal with the decoherence, we introduce additional sequences in the middle, which actually reform first, remove the spatial dependence, and then bring it back such that we have phase matching upon readout. So the protocol that we use has pulses right after writing and right before reading, which first remove and then restore this spatial dependency, such that it is not present during decoherence. You can imagine this in the following way. We have this wave vector that we need to remove. We apply 2 laser beams here, an additional transition, which gets us to pretty much 0. So this is drawn as essentially 0, and then we bring it back right before readout. And again, I remind that this is here much bigger problem than this tiny wave vector. This was in the ground state configuration. All right, so in practice, we use laser beams with different frequencies and different polarizations, such that we in fact transfer the spin wave such that it starts as being a spin wave between F2 state and the Rydberg state, and in the meantime is a spin wave between F equal 1 state and the Rydberg state. And we are able to improve the lifetime at the cost of some inefficiency, which is related to the time that it takes to do this operation, from around 1 microsecond to 30 microseconds, which is already limited by the natural lifetime of the Rydberg states. So this is our full configuration. We have this spin wave freezing beams. We have the probe and the coupling. This gets stored in the atomic ensemble. And we also have a microwave here, which allows us to transfer atoms between the state with orbital d and the Rydberg state with orbital p, which we'll call the typical with d and p. And if we do that, and we kind of we encode this microwave in between here, then we see Rabi oscillations directly using the EIT protocol. However, let's now see what happens if we also introduce a time delay and allow the atoms to interact. There isn't really a switch for the interaction, but it's just a time delay. If we do that, then it turns out that we no longer get a nice Rabi oscillation, but our oscillations start to look like a cosine or sine to some higher power. So the sine, the one and the other port don't add up to 1 anymore, unlike sine squared plus cosine squared. And the more photons we have, and the longer the wait time, the stronger this effect gets. So now we had an idea, okay, so this is sharper now. Let's use it for the metrology of the microwave field. But before we do that, let's understand what's happening. So to understand what's happening, we designed the following experiment. Instead of just doing the Rabi rotation, we do the Rabi rotation with some angle theta. We allow the atoms to interact, and then we restore the rotation by exactly the same angle theta, such that when the atoms interact, then they are, statistically speaking, in a superposition state between P and D at some angle. And it turns out that the decoherence is stronger the more superposition style we are. So if we increase the angle until pi half, this is where the strongest decoherence happens. And in fact, if you measure more, if you do a pi rotation such that you go to from the purely from D state to the P state, then you again do not have any significant decoherence. Well, signal drops, but the decoherence is largely removed. So here comes our idea for the explanation. And clearly, there are dipole-dipole interactions involved between the P and D states, because it only happens when we have both. So we have the following idea. We start with a Hamiltonian, which hops the atoms between the P and D state with the following strength. And I regret to say that we do not have a full solution for the many-body problem. However, we have a certain explanation. So if we start with a symmetric state that has same spatial dependence for the P and D atom, so those psi and mu are P and D atoms, then this will remain in the symmetric state given this interaction. So we can just solve the Schrödinger equation for two particles, one P, one D style. So we have a very nice solution, which is just a phase term. So if we now agree that this is usually just a phase term, unless we have some many body, some kind of free body correlations. So as long as those are two body correlations, we should just have a phase term. Then we can just take this wave function and calculate, okay, so what will be the contribution to the readout, which we need to integrate this state over a phase matching condition. So this is our result. We just need, the solution is simple, but the integration that we need to do on the solution, not so simple. But it turns out very nicely that we can just solve this integral. And given a few rather well-justified approximations in which we assume that the interaction doesn't stretch very far outside of the atomic ensemble, let's say, we are able to get a very simple solution, which tells us that this decay, at least for the interaction that, well, again, doesn't immediately cover the entire ensemble, is actually a linear decay in time. Now, nicely enough, if we have a linear decay in time and we have n atoms that decohere the spin wave, then we can make then we can assume that those decoherences are independent, and we have an exponential decay with a rate that is proportional to a certain volume expansion divided by the volume of the entire ensemble. And it turns out that this volume expansion coefficient is, of course, proportional to the C free constant of the dipole-dipole interaction. So very nicely enough, this interaction, I consider it to be a somewhat long-range interaction. Why? Because the influence sphere of this decoherence grows linearly with time. So the volume grows linearly with time, so it never slows down. And I can make an animation on that also, that let's allow it to play. So there are some Rydberg atoms of the P style, and they imprint a phase on the D-type spin wave, and this spin wave gets completely decohered everywhere there is a Rydberg atom. So overall, and this keeps growing with time, just keeps growing and keeps expanding. So that's our interaction, and nicely enough, we can also estimate that this growth rate is about 1 milliliter per second per atom. So a very absurd amount because we are dealing with microseconds and micrometers, but you can also express it as a kind of drop rate. All right, so we have a result. So we have a certain phenomenological model, I would say, that involves the two-body correlations, and we can write it as a general, we can now predict those curves, and we can write it as a general Krauss operator set that describes the interaction. So let's test it on two excitations. So if we have two excitations and they get Rabi rotated, then we get a combination of state 2, 0, so both in D state, 1, 1, dp, and 0, 2, everything in P state. Now our interaction will decohere the terms which involve both states. So the 1 gets decohered. So this gets removed. And it turns out that is an excellent thing for metrology, because if this term could, when losses are involved, and there are always losses in this system, this term decays to 1, 0, and 0, 1, and thus generates noise. If we can avoid that, if we introduce an additional loss and remove this term, we enhance the distinguishability in the fog space, and not only the sine and cosine here get sharper as predicted, but also we improve the Fisher information of the estimation in the particular point, which we can always tune to use. All right, I'm almost done because now we just need a small metrology context. So you would normally think that the Fisher, the naive limit for the information you can get from each photon is the efficiency of the systems times the quantum Fisher information. However, we can get more per each detected photon. And of course, we don't get more than quantum Fisher because we have a big inefficiency here. But we get more per each detected photon by introducing a certain error correcting or error mitigating nonlinear loss here. And in fact, we can get significantly more. And the final result is that we actually perform the estimation with my maximum likelihood estimator. We try to unbias everything. Everything works very nicely. And we are able to improve the precision or improve the Fisher information by a factor of about 3. And I think this is a very interesting error correction protocol in a way that has perspectives to be also used in much more complicated contexts, especially in the Rydberg atom arrays, where we could not only look at many body correlations, etc., but also consider how to do metrology even with a quantum algorithm rather than just considering the Fisher information. All right, thank you very much. And I also have an opening which in a grant that is involved with that, which can be both a theory or an experimental position. Thank you.
Thank you very much, Michał. Questions? Okay, I will start with one question from. So just coming back to the last part when you show the two excitation protocol, no, which you now you say that okay, you have the 1 component naturally goes away.
Yes.
And then you need to eliminate them. But this, so you have no effect, no small decoherence effect, dephasing between the 0 to 0 component?
Not due to this kind of interaction. So overall, the system has an experimental loss. So the efficiency of the detection at the end is just 2% in practice. So everything gets lost. But this happens after this interaction. So in fact, we strongly believe that those parts are unaffected. They could be a little bit affected by the van der Waals interaction, but because we are in a rather low Rydberg state, around 50, then the dipole-dipole interactions are much dominating over the van der Waals interactions.
Okay, thank you. Let's see if there is some further question. If not, let's thank Michał again.